Hello together. Today I want to do the simulation of our example. We had one example. This was the example of a lossless two-port where we did discuss the absolute value condition and the phase condition. And of course this example we can also solve by using our simulation tool. And as you know, the simulation tool you can download from the homepage, which is associated with this YouTube channel. So what we discussed in this example was we considered inductance, which is connecting two transmission lines. And this inductance has a value of 20 nanohenry. The characteristic impedance of the transmission lines is 50 ohm, which is also normally the characteristic impedance of a network analyzer. And we consider this next to or around 100 megahertz. And if we do the simulation, in our simulation program we have at least these two diagrams or charts. We call one diagram is called LinMag and one diagram is called the LogMag diagram. And these are normal diagrams which are also available in commercial network analyzers. And if I have a LinMag diagram, the parameter, for example, S11, the absolute value of this parameter, which is just a number and which normally is always smaller than 1, is displayed in, I call this, in the linear scale. And if I have a LogMag diagram, then we will display not the S parameter itself, but we will display 20 log S11, and then we say this is S11 in dB. Of course, from a mathematical point of view, this equation essentially makes no sense because we have 2 times the same value here, but I will not always introduce another parameter, so I use always the same parameter, so I come more from a physical view, and due to this physical view I say I can display, of course, S11 in a linear scale, or I can display S11 in a logarithmic scale, and then we say S11 is given in dB. And now we can start with our simulation.
Together, today I want to solve the example of the lossless two-port with the help of my simulation tool. And to start the simulation, we take an inductor here and put it onto the circuit board, and we can change the value of the inductor to 20 nanohenry. And as measurement equipment we again use our network analyzer, and we put the network analyzer here, and we connect the network analyzer with the connections to our inductor. And according to our example, we had to analyze the lossless two-port with a center frequency of 100 megahertz. So we changed the frequency to 25 megahertz, and this is the start frequency, and the stop frequency we will change to 175 megahertz. So 100 megahertz is just in the middle of this frequency range. And of course now we can already do the analysis of this, and we find here now, for example, the parameter S11 again in the LogMag scale. This means the parameter S11 is given in dB, And we can read out, of course, the value at 100 megahertz using the marker function. And with the help of the marker function, we find that at 100 megahertz we have S11 absolute value of minus 18.08 dB. And you can, of course, check now by yourself if this corresponds to the linear value we already got in the example. But we also can change this or find the linear value using another format. So I will change now to the LinMag format, which means now we have a linear scale for the absolute value of S11. And here we have the reference line of 1, but we have a value of 0.05 per division, so we can increase this value, for example, to 0.1. And now we change the reference position. So the reference position is here now, it's 1. And we can now also use the marker again to find the value at 100 megahertz. And here we have the value now, and in our approximation we got a value of 0.126, and now with the correct simulation tool we get a value of 0.125 roundabout. So this is very near to our approximation we already got in the example. And of course we can also, for example, change the reference value and the reference position, for example, like this. So now I want to come to the parameter S21 in a linear scale. And now, of course, I will change the reference position. So we have here the reference value of 0.7. Perhaps I change the reference value again and the reference position. So we have now the reference value is 1 here, and we have a 0.1 per division, and we can read out a value of 0.9922, which almost exactly corresponds to the value we already got in the example. The main difference we will see in the phase. So in the example we got a phase of S11 which was 90 degrees, so I must now change again the parameter to S11, and I want to change the format now into a linear phase diagram. And now we have here again the reference value is 0 degrees, and we have a 10 degrees per division. So what I will do now, first I change the reference position here, for example like this. So we have here 0 value, and now you will see that we have roundabout here, we will have the 90 degrees. And if I again now use the marker function, I can get the phase of S11 at 100 megahertz, and then now you see that we have a difference to our approximation. Our approximation predicted a value of 90 degrees, and here we have now a value of round about 80 degrees, so a difference of 10 degrees. We can also have a look to the parameter S21, and again we can have a look to the value. So we have a reference value here again of 0 decrease here, a 10 decrease per division, and in our approximation we assumed that we have a value of 0 decrease, but now you see the simulation tells us we already have here a value of -7 decrease, which will be the phase of our parameter S21. So this finished now our example of a lossless two-part.